Well, it's a great pleasure to be here. I'll just point out at the beginning that my slides are available on my website, dataviz.ca, under papers. So I'll introduce my co-conspirators to you today, Heather Turner, David Firth, Akim Zealous. I show their pictures because I've never met them. Our correspondence has all been by email. So I'll structure my talk today around the content of 3 R packages related to the topic of visualizing categorical data. And I'll begin with a brief history of what I consider visualizing categorical data. I'll start with some papers by John Hartigan and Beat Kleiner in 1981-84, where they showed a 4-way Mosaic display of a 4-way frequency table. So what you're seeing in the cells is the number of viewers of television programs classified by day of the week, time of day, and the station that they were watching. Now, it's a lot of information there, but what I was particularly attracted to was the idea that you could even do this, that you could even have a way of visualizing a 4-way table. Not to say that I can really understand what is going on here. I thought about this for a while, and I realized that there's a very close connection between log linear models and these frequency tables, and then one could actually visualize both the frequency in cells of tables by use of area, together with the residuals from some particular log linear model. I first presented this work at Carme in Cologne, for which I'm grateful to Michael and Jorg. And what you see at the bottom are 2 Mosaic displays, one of a 2-way table, one of a 3-way table, hair color by eye color by sex. And I'll just point out for now that what you're supposed to pay attention to here is 2 aspects. One is that the area of each tile represents the frequency in the cell, is proportional to the frequency in the cell. And the second point is that the coloring, the shading of the cell, shows the residuals from a particular log linear model. That is, deviations from independence in the case of the, where's my cursor? The other mouse. So here, the cells shaded blue are those where the actual frequency in the cell is greater than you would expect under a model of independence. That is, blue shows greater than expected frequency, and so the pattern, and red shows less than expected frequency, and the pattern of the association is shown by color. So what we see here is that there is a great preponderance of people with brown hair and black eyes, and also with blonde hair and blue eyes. Here is the same data, but now broken down by sex. Empty cells, the residuals or lack of independence is within a certain plus or minus 2, so there is essentially no residual association there. So I worked on this for a while, and I wrote my book, Visualizing Categorical Data, using SAS software to develop biplots, correspondence analysis, Mosaic displays within SAS. But of course, Mosaic displays and these other things have a much longer history. So in fact, here's the first exemplar of what I consider a Mosaic display, a flashing diagram, an area diagram, with 2 splittings. And then we have things such as Birch, another area-based display. In 2002, I met Kurt Hornick at the American Statistical Association, and I said, what would it take to develop Mosaic displays and other visualization methods in R? I gave him 3 copies of my book. Great investment. He and 2 of his students developed the VCD package, which I'll be talking about today. So let me give you a visual overview of the content and my particular take on visualizing categorical data. So let me start with what I hope you'll all agree is the central goal of data analysis and statistics. That is, we start with some data. And the goal should be to tell a story, tell an accurate, understandable, and hopefully interesting story about what is going on in some real problem. Well, there are at least two paths to do that. One is an exploratory path based on visualization. So there's a variety of visualizations directly from going from data to, hopefully, to some story. Another path is model-based. And I'm not saying that these are mutually exclusive, but it may be that a visualization suggests a particular model that would help understand, explain what is going on in some data. Of course, when we fit a model, we summarize it, and any summary, any model summary, is really a smoothing of the data. And I think that's important to understand. So we can go from a model summary back to visualizations of a smoothed relationship. So, for example, we have a scatter plot and we fit a regression line. The regression line is a smoothing, but we can have more complex smoothings. But at any rate, we eventually get back to a story. So I'll be talking about models for categorical data, and I'll focus on three nested classes of models. The most basic models for frequency tables are log linear models. But of course, log linear models are just a special case of generalized linear models with a Poisson link, and there are ordinary linear models are just other exemplars of generalized linear models. And we have also generalized nonlinear models. My goal in this work is, in every case, to connect models with interesting, hopefully useful visualizations. So this will be a tale of three packages in R. The VCD package provides a general structure for visualizing categorical data. The GNM package extends generalized linear models to generalized nonlinear models, and in fact makes the fitting of these models easy to specify and easy to think about. My VCD extra package really provides glue between these two, introducing Mosaic displays for generalized linear and nonlinear models, 3D Mosaic displays, and a few other features. So let me begin with the VCD package, and I'll talk about some extensions of simple Mosaic displays. There's a variety of them. Pairwise displays, such as a scatter plot matrix, that framework, that visual framework, can be used in a variety of ways to show marginal, bivariate marginal views, as in an ordinary scatter plot matrix of quantitative data, conditional views and partial views. Other people have suggested variants of Mosaic displays. The patterns of residual shadings that I've developed have been extended to show not just the pattern of association, but significance, either statistical significance of an overall model or significance of individual cells in a frequency table. And of course, there have been developments of dynamic interactive versions, which I think are fundamental for actually using some of these methods, particularly with complex models. So let me now talk about the organization of the VCD package for visualizing contingency tables. It recognizes the fact that there's quite a variety of instances of displays, different types, different principles, different construction methods for showing n-way frequency tables. Yet there are certain commonalities. They all have to do with representing n-way tables in two dimensions. And I don't mean a 2D model or a 3D model, but rather the restriction of the plane of a piece of paper or a computer screen is always 2D. All of these methods use area as the metaphor to depict frequency. Some of these are model-based, and that is to say that they are designed to give a visualization of both the data and some statistical aspects of the data. And they all use visual attributes, color, shading, to highlight relevant statistical attributes. So let me begin with a trite, hopefully familiar data set on admission to graduate programs at University of California, Berkeley, classified by gender, admission status, and the department to which people applied. I'll just point out that this is a tabular display, uses a model formula, and if we simply omit one variable from the table, automatically we get the collapsed marginal table over that. So at the bottom is the marginal table of admission by gender. Some general ideas about visual display in the simplest possible case for the 2x2 table of admission or rejected by gender in that Berkeley data. So at the bottom we see what's called a fourfold display, and the principle of construction is that, again, area represents frequency, so the size of each quarter circle is the square root of the frequency. The area is therefore the frequency. Independence is shown when adjoining quadrants are adjacent. So the proportion of males admitted compared to the proportion of females admitted. If there was no difference in admission rates, those two would have the same area. Shading, color, is used to show the direction of positive association, and what we see is males are more likely to be admitted, females more likely to be rejected. But in fact, this is a visualization, an exact visualization of the odds ratio. The odds ratio in this table is exactly the ratio of the area of the blue cells divided by the red cells. And there are little bands around the quarter circles, and those are actually confidence rings for the odds ratio. So the statistical property is that the confidence bands will overlap if the odds ratio is not significantly different from 1. Otherwise, it will not overlap. And of course, we could have higher weight tables, so I'll call these stratified tables, but this is really a three-way table. The original data, admission by gender, by department. And now you see that I've used shading to indicate which of those 6 panels has an odds ratio significantly different from 1. And it turns out only in department A, where in fact the pattern of association is that females in this department are more likely to be admitted. In all of the other departments, the direction is not always the same, but you can see that in every case the confidence circles do overlap and the odds ratio is not significantly different from 1. Mosaic displays, I'll just illustrate what I call friendly shading, what is called in the package friendly shading. So the idea, again, is area is shown by, it represents frequency, and I use a scheme red for cells whose residuals are negative, that is the Pearson residual, the contribution to the chi-square statistic is less than 0, versus blue for positive association. And I use a simple 3-step shading scheme. So light blue represents residuals between +2 and +4. Dark red or blue represents residuals greater than 4. White, residuals less than 2. Other shading schemes have other properties that I won't have time to talk about today. So here is fitting the model of mutual independence. There's no association whatsoever in this 3-way table, admission by gender by department. Again, focus on the pattern of red and blue. That shows the actual association, that is, the association not fit by the model. This model obviously fits fairly poorly, so we can go on and fit a more refined model, a model that says that admission is independent of the joint combinations of gender and department. The shading in this Mosaic display, therefore, shows the extent to which that is not true. That is, the extent to which admission depends on department or gender or the combinations of department and gender. Again, this model does not fit well. There's a lot of shading. But if you look at the pattern of red, blue at the bottom versus blue, red at the top, you see that there's something going on here. So we could fit a more detailed model that allows for associations of gender with department and admission with department, but asserts that there is no association of admission and gender conditional on department. And now this fits fairly well, except for department A. So the idea of that I like to think of as visual fitting, getting a better fitting model, is cleaning the mosaic. Removing the shading means we have a good fitting model, and therefore a better explanation. Here's another variant of Mosaic display called a double-decker plot. I'm going to go kind of skip quickly through some of this. And now let me move to the struct plot framework. Whoops, what did I do? I clicked the wrong thing, the wrong clicker. Okay, so the struct plot framework makes all of these kinds of displays coherent. You can fit any log linear model. There are high-level functions and low-level functions. And the key thing is that all of these work through a single function, which is called struct plot. Mosaic displays, association plots, sieve diagrams, pairs plots, all of these are built on top of that. Beneath that, all of the details, labeling, spacing, shading, these are all provided by low-level functions. So here's my shading friendly. Here are some other shading functions. There are other spacing functions, et cetera, et cetera. So this provides a very general scheme. We can, for example, look at a variety of different bivariate, pairwise bivariate views. A view showing essentially a visualization of the BERT table is simply all pairwise plots together with the univariate margins. But we can also have other things above the diagonal or below the diagonal. This center plot is actually showing the model of complete independence of all three variables in three different ways. Now, there's a lot there to look at, and I'm not going to go into very much details. And again, I clicked the wrong thing. But here is the just an example, a pairs plot asking for mosaics in the diagonal panels. Okay, so I'm going to move on to towards generalized linear models. And let me just point out that log linear models have simple modeling formulas, and R, the model of independence, is essentially A plus B. That is, those are independent in the log linear model, whereas the saturated model has A plus B plus an interaction. But these are fit using iterative proportional scaling, and therefore there's a limited syntax, and there are no standard errors available. Generalized linear models extend this to linear function connected with the mean, that is the frequency in the cell, by a link function. And log linear models are essentially GLMs in the Poisson family. A generalized nonlinear model is really the same as a generalized linear model, except that the link function can be nonlinear, and nonlinear in the parameters. So these essentially simply combine classical nonlinear models with the standard forms of generalized linear models. But in the context of categorical data, these provide great benefits. So we can have simplified models for structured associations, models allowing multiplicative association, for example, the Goodman RC model, multiple instances of multiplicative terms. An RC2 model is really analogous to a biplotter or has a close relationship with correspondence analysis. And one can, in fact, define their own functions. So here are just some simple examples of the syntax for generalized nonlinear models. For square tables, for example, individuals classified by their occupation and the occupation of their offspring, we might want to ignore the diagonal cells. We're interested in mobility, not the fact that sons and daughters tend to follow in a similar category to their parents. We might suggest a model of symmetry. If someone is one step removed from the occupation of their children, there's a similar frequency in the above diagonal cell, and so forth. So all of these are actually generalized linear models, but the GNM package makes them quite easy to specify. So here are some examples of nonlinear models specified by functions of class nonlin. And the basic functions are exponential, inverse, and multiplicative. But the important thing is that these can be combined in arbitrary ways to express essentially any nonlinear model. So for example, a model that for a three-way table that says essentially that there is a common pattern of association between, let's say, the rows and columns of the table, and that association is moderated just by multiplying by a single parameter for each layer in the table, is specified as multiplicative of exp of c and a comma b. Goodman's RC2 model with two multiplicative terms is specified as simply two instances of these multiplicative terms. And the important point is that all of these nonlinear models are fully general. They provide all the things that you might want, residuals, plots, fitted values, etc. The VCD package, VCD extra package, as I said, provides glue between these two. So there's a mosaic, really a mosaic method for GLMs and GNMs, sieve plots, association plots. Often you fit a large number of models and you want to collect them and analyze them as an actual class. So there's a GLM list facility as well. So let me take up some examples dealing with models for ordered categories in three-way tables. And I'll start just simply with two-way tables and just suggest that between the model that says the association between rows and columns is completely unstructured, that is, the full two-way association, there are a variety of simplified models going down to a model of uniform association that says all of the association is described by one parameter. And that turns out to be something like an average odds ratio. Between those two extremes, there are models that use integer scores for the columns, but estimate scores for the rows. The reverse situation, or a model that has that uses both scores for the rows and scores for the columns, but estimates row and column effects. And the RC model is in here. So this is like a one-dimensional correspondence analysis. Okay, so here is an example. It's a three-way table. Father's occupational status by sons. The occupational categories are upper non-manual, lower non-manual, upper manual, lower manual, and farm. For the US, the UK, and Japan didn't fit on this slide. There's a demo in the VCD package. So, of course, I'm coming to Carme. I can't come to Carme without a multiple correspondence analysis. So here it is. At first glance, I was quite happy with this. It seems to me that the first dimension, 52%, is interpretable as a distinction between farm people and everybody else, whereas on the second dimension, there seems to be an ordering from father upper non-manual down to sons lower manual according to occupational status. And in every case, the blue point for the son is higher than the red point for the father. So I said, oh, that sounds great. But then I thought, well, how does this actually relate to sociological theory about social mobility? And that was not at all clear to me. I also couldn't see how to interpret the country effect. So we have Japan way out over here, US in the middle, and UK over here. So let me describe some models that I would fit to this data. And let me start with baseline models. So the simplest model asserts fathers and sons are independent. But there are differences across countries or layers. That's a model of perfect mobility. But we're maybe not interested in the diagonal cells of the tables, so we simply add a diag RC term to essentially fit those exactly. Now, the interesting thing is that these baseline models can be combined by a nice algebra with any models for the layers. So we might say, well, it's the same pattern of association in all countries, homogeneous. Or we might have various models describing, fitting a simplified association in the three-way table. So the simple example that I'll cover today is a general pattern of association between rows and columns modified multiplicatively by a term for each of the countries. So the association may be greater in the UK than in the US, than in Japan, and there's an actual parameter that's estimated. So here are the model formula in a simplified way for those cases that I considered before. So here's just an example of fitting these models. The null model, father independent of son independent of a given country, is simply father plus son star country. And the important point I'd like to draw your attention to is that we simply fit a model and then use the Mosaic function to show that model. So here is the model of perfect mobility. We can see a clear pattern of association in each of the countries. The size of the display is proportional to frequency. There are very much less total frequency in Japan, so that's sort of squished. But we sort of see a diagonal pattern here. Well, we're not really interested in the diagonal cells because we want to study mobility, ignoring the fact that probably most sons end up in the same occupational status categories as their fathers. I'll just show you how simple it is to fit a wide variety of models to these data. So the models allowing particular forms of interaction, of association between fathers and sons, rows and columns, are specified by simple update methods, starting with the model of quasi-independence, adding terms for father by son score etc. And here are some examples. I'm not going to go into the details, but you can sort of see that there is still, although these models fit better, there is still some residual lack of fit in the model here, which is a model of row effects. Here's an RC1 model that looks somewhat better. At the top are how you would fit the extended models allowing heterogeneous association. But the general point I'd like to make is that because these fit as extensions of ordinary GLMs with simplified model formula, all the summary methods available, print methods, summary methods are available, extracting coefficients, residuals, etc. And we can get simple diagnostics, residual plots, etc. By saying plot model. We can get mosaic displays and other visualizations by saying mosaic of the model. We fit a bunch of models here. How are we going to compare them? Well, GLM list is a function that simply takes the names of a set of models, collects them in a list, and then you can do a variety of things with those lists. So summarize for a GLM model list gives a convenient summary of the chi-squares, p-values, AIC, and BIC. And then we can take that and extract, for example, the BIC statistics and make a plot. And what we see here is sort of interesting. The log multiplicative models are less preferred according to BIC than the homogeneous models. There seems to be little difference among the column effects, row plus column, and the RC1 model. But if we look at AIC instead, we get a different story. In fact, here the log multiplicative models are slightly preferred by AIC. Now, I don't want to go into the details here. I just want to make the point that in this framework of a model-based framework, these kinds of methods provide a simple way of comparing a set of competing models that will provide some, hopefully, story about the data. 3D mosaics. I'd wanted to do this for a long time. So log linear models are based on the fact that log frequencies are additive, frequencies therefore are multiplicative. Mosaic displays use that fact. So tiles are row height by width, giving area as the contribution. And so we can sort of see here that if we make a plot showing area showing expected frequencies under a model, we get a perfectly rectilinear display. So how to take that to 3D? Well, there's a lovely package in R called RGL. And here are 3D mosaics for the hair color, eye color data, showing on the left the observed frequency as areas of volumes of the tiles. Here showing expected frequencies, and these are fully manipulable. Now, as far as a use for them, that's sort of still to come. For now, I'm happy to be able to make pretty pictures. Okay, my final topic. How am I doing on time? Good. My final topic, models and visualizations for log-odd ratios. So an odds ratio is a ratio of two odds, and in terms of a two-way table, we can calculate, that is an R by C table, we can calculate the odds ratios for adjacent sets of categories. All R minus 1 times C minus 1 adjacent sets of categories. But we don't have to use odds ratios of adjacent categories. We can use any one of a number of other reference set of categories. So, for example, comparing I to the last row R and J to the last row C. Those give an equivalent but different set of log odds ratios. I'll just point out that my interest in this is that many models for 2, 3, 4-way tables have a much simpler form when expressed directly in terms of odds ratios than, for example, as a log linear model or as a generalized linear model. So the model of uniform association, shown here with fixed scores for the rows and fixed scores for the columns, a single association parameter, what that really means is that the odds ratio for all adjacent categories is a constant. It's a very simple model. A single number describes the whole pattern of association. And my point here is that direct visualization in terms of odds ratios actually provides a simplified version of a way to look at patterns of association than area-based displays. So I'm going to skip over the algebra here, except to point out that the computation of log odds ratios in the general case of an R by C table with any number of stratifying factors has a relatively simple form, implemented currently called L odds ratio in the VCD extra package. There are methods to extract coefficients, variance, covariance matrix of the log odds ratio, confidence intervals, fitted values, etc. Now, once we've calculated log odds ratios these represent all of the association in a two-way or higher way table, we can think about fitting linear models for those log odds ratios. And it turns out that the log odds ratios are normally distributed with a variance-covariance matrix that has a highly structured form estimated from the data. And so we can simply calculate, fit any model for the total collection of log odds ratios as an ordinary linear model by generalized least squares. And as a result, what we get are standard R objects. And those standard R objects have print methods, summary methods, plot methods. So for plotting any complex table of log odds ratios in relationship to a model, there's a variety of methods already out there. So let me go through two quick examples. So here's some data on the association between two symptoms that coal miners may suffer. One is breathlessness, and the other is wheeze. And what you see here are fourfold displays for age classes ranging from 25 to 29, the youngest age class, down through 60 to 64. Now you can see in every case those two symptoms are strongly positively associated. If you have breathlessness, you're likely to have wheeze, and vice versa. But can you see a trend here? Can you see what the pattern of association and how that changes over age? I can't really. All we have to do is calculate the log odds ratios, and here I've fit a linear model. LOR is the log odds ratio in relationship to age. This variance-covariance matrix is diagonal, so I can just use weighted least squares. And here I fit a polynomial model in age and age squared. And then I can do simple tests, and the analysis of variance tells me that the quadratic model doesn't provide a significantly better fit than the linear fit. But here I can simply visualize the log odds ratio. So this is a positive number, means that having breathlessness is associated with having wheeze. And the higher the number, the greater is the degree of association. Here are the actual odds ratios, and blue is the linear model red is the quadratic model. And it actually looks like the red model is a little bit closer to the points. But you can sort of see the standard errors are large enough that a specific test of whether the quadratic model is a better fit, it turns out to be non-significant. So here's another example, a four-way table now. And it concerns attitudes about whether you should use corporal punishment for children. And the two classes are, yes, moderate corporal punishment is okay versus never. Another variable is whether the person recalls having been punished as a child, yes or no. Education, their level of education, age group, and arguably, in this case, a model for attitude as a response variable might be a useful thing to do. But here I'm going to focus on, is attitude about corporal punishment associated with their memory of whether they were punished as a child in relationship to age and education. So here are the frequencies. You can see that some of them frequencies are fairly small. Here's a set of Mosaic displays. The COTAB plot in the VCD package can take an arbitrary panel function in a trellis-like display. Here's a plot and the calculation of these log odds ratios. And now the pattern is really clear. We see that in the two young groups, as education increases, there is a stronger and stronger association between attitude about corporal punishment and their memory of whether they were punished as a child. Whereas in the 40-year-old group, the pattern of association is the reverse. Now, the standard errors show that maybe that's not like a really strong claim because there's a lot of slop here. And so we would actually need to fit an actual model and test it. But at any rate, this is a new direction now being developed in the VCD extra package. So, my summary slide. I started with the idea of going from data to a story, two different routes, visualization versus model fitting. And really what I've shown throughout is combining those two routes. But in order to be able to do this, I think it's really important that the visualization be general and really easy to do. Second, it has to be easy to fit complex models. So the VCD package does provide this general framework for at least all of these area-based visualizations. The GNM package extends the class from log linear to generalized linear to generalized nonlinear model, and makes it easy to set up and test models for structured association, models that are more parsimonious than simply the display of the raw frequencies. We want something like that serves as a summary or a smoothing of the data. The VCD package provides the glue and a test bed for the development of new visualization methods. So I thank you very much for your attention.